we will deal with buckling of inhomogeneous structures. Columns. So we dealt already with one problem, and that is buckling of this column, simply supported column, P. And we had this governing differential equation like this. X over L equals xi. Then we had d2 d xi square, d of xi, d2 w d xi square plus p critical L square d2w d xi square. And I considered in much detail simply supported column. So where w must equal psi of xi, and that equals, I think, xi minus 2 xi cubed plus xi in fourth power. So we got the following. We got P critical equals minus 12 B2 over L square. That means B2 must be negative. Then we got D of xi, which equals B0 plus B1 xi plus B2 xi square. And this equals minus 1 minus xi plus xi square B2. Now this B2 is negative, must be negative. Therefore I can write down D of xi equals, I can take out this minus, so it will be 1 plus xi minus xi square, and here is minus B2. Minus B2 is then absolute value of B2, because I said that B2 must be negative. So therefore D of xi equals 1 plus xi minus xi squared B2. And P critical, which equals minus 12 B2 over L square, this again minus B2, so it will be 12 B2 over L square. Okay? We can also write down like this. D of xi, D at 0 equals absolute value of B2. Therefore, this can be substituted there, and we can write D of xi equals D of 0, 1 plus xi minus xi squared, and P critical equals 12 D of 0 divided by L squared. Okay? Then I asked you to do at home some homework. Homework you had. Clamped. Beam, a column. Clamped. So then psi of xi equals xi squared minus 2 xi cubed plus xi in fourth power. I'm giving you results. I do not give derivations here because that was a homework. Okay, then I hope that you received the following response. P critical equals minus 12 B2 over L square, and then D of xi equals 1 6 plus xi minus xi squared, So that is minus B2. Okay, I hope that this is the result. Now, B2 again must be negative. So P critical can be written as 12 absolute value of B2 divided by L square. And D of psi then equals 1/6 plus psi minus psi square, absolute value of B2. Okay, now here there is a question that could be posed. For simply supported beam, we got P critical equals 12 B2 over L square. For clamped, we got P critical again equals 12 absolute value of B2 divided by L square. Question, how it is possible? Okay, the same expression. For buckling load. Sounds paradoxical. Did you ask this question to yourselves? Yes? Okay, one listener is telling me the following. Answer. Student says, possibly because of symmetry. So we have simply supported. We have clamped. Symmetry means the same boundary condition at both ends. Okay, so refutation. For homogeneous beams, homogeneous columns, look, we have that is simply supported, and this is clamped. Here, P critical equals pi square EI over L square. Here, P critical equals 4 pi square EI over L square. So there is the same symmetry. But factor of 2, factor of 4. Okay, so that is what is happening. So symmetry cannot explain. The paradox. Any other communications? Can you speak louder? Yes. Yes. So another student. B2s are, let's say, coefficients B are different. So let us see this. Let us put this in. So simply supported, clamped. So we have here d of psi equals 1 plus psi, 1 minus psi plus psi square b2. That is in that case, and simply supported case. And here we have 1/6 plus psi minus psi square b2. So then P critical equals 12 b2 over L square, 12 b2 over L square. So what happens here is as follows. These are different beams. So different beam or different columns. Different columns can have the same buckling load. So for example, homogeneous case, say simply supported. So P critical equals pi square EI1 over L square. So EI1 is stiffness for simply supported column. Now clamped. P critical equals 4 pi square EI2 L square. EI2 equals stiffness for clamped column. Now, if EI1 equals 4 times EI2, they will have the same buckling load. Okay? So that is possible because these are different columns. That is one observation. Second observation. Can I cover this part? Okay, I will write down. For simply supported, d of psi equals 1 minus psi plus psi square b2. And for clamped, d of psi equals 1/6 plus psi minus psi square b2. I hope I did not make mistakes. Yes, that's correct. So we can ask actually the following question. Find such the average so that in homogeneous columns buckling load equals the homogeneous columns buckling load. With the average. Okay, now what is the average? The average will be integral from 0 to 1 of this d of psi, d psi. I'm integrating this d psi. So I'm getting integral from 0 to 1, 1 minus xi plus xi squared, b2 d xi. So this equals. So when I integrate 1, I get xi. Xi, that means 1. And 1. When I take this term minus xi squared over 2, so that will be 1/2. Plus, then it is xi cubed over 3, so 1/3. Okay? And that is b2. So that equals 6 minus 3 plus 2. 8 minus 3, that's 5, 6. The average equals 5, 6, b2. So we can write that b2 equals then 6/5 of the average. So buckling load will be P critical simply supported equals 12 b2 over L squared. That equals 12 over L squared and 6/5 of the average. So that will be how much? 72/5 the average over L squared. Now that is for simply supported. For clamped, the average equals. So it's 1/6. So it will be 1/6, then plus 1/2 minus 1/3. B2. 6, that is 1 plus 3 minus 2. 2, 6, so 1/3 B2. So what we get then is as follows. B2 equals 3D average. I hope you are paying attention, and I hope that I'm not making mistakes. So then P critical here equals how much? 12 B2 over L squared. That equals 12 over L squared, then B2. B2 equals 3D average. Or 36 the average over L squared. So now you see in terms of the average, if the average value of D is the same, then P critical clamped divided by P critical simply supported will be 36 divided by 72/5. Okay? Or it will be 5 times 36 divided by 72. Or it is 180 over 72. So it is not 4 times, but approximately 2.5 times bigger. If they have the average the same, we must be able to compare in some sense. So it's approximately 2.5. So it's not 4. Okay. So conclusion here is very simple. Once results are obtained, they must be digested. So what we did was we asked, why do we get the same expression? So it's not. So these are different beams or different columns. Seven. What is our topic number? 42. Buckling of inhomogeneous columns under their own weight. So columns naturally can buckle if they are sufficiently long. So this is this clamped free column. So first time, this problem for uniform beams, uniform columns, was considered by Euler. I'm not bringing a solution. It is written in terms of Bessel functions. Okay? Then, I think that was, I don't remember which year was this considered. Then in later, yes, in 1778, Euler considered the following problem. And this is simply supported. And there is this, I said here P, but let us write Q, small q, because that is intensity of loading. So this is Q. Yeah, by the way, in this particular case, this Q equals 7837 EI over L cubed. And it is obtained by Bessel functions. If someone is interested, you can read it in the book by Timoshenko and Gear, 1961, Theory of Elastic Stability. Okay, this problem. I'm not going to deal with this. Then in 1778, Euler considered clamped simply supported column. Now he published 3 papers. So 1778A, 1778B, 1778C. Okay? All in Petrograd proceedings of Petrograd Academy of Sciences. Petrograd stands for St. Petersburg. Okay. Now, the same topic he dealt in 3 papers. Now, this is an interesting history. In 1778A paper, he concluded that column never loses its stability. Never. So there is no such no critical. Q critical does not exist, or it is infinity actually. Q critical can be anything. I mean, any very big number. never loses its stability. Now 1770 B paper. He says, my previous result is suspicious and paradoxical. Means that cannot be, he said, that suddenly this column does not lose its stability. I mean, why would that be? Then in 1778 C, he found a mistake. And found Q critical. Q critical, he found 200 EI over L cubed. Now, Dinnick in 1912, so 130 years later, showed this result means Q critical equals 200 EI over L cubed was wrong. Okay? So after many years, it was shown that it was a wrong result. Because what happens is that Euler, he has his determinant and he wants to find the root. So he found the second root, which is 200, but omitted, did not find this 18.6 root. He overlooked. So this, he has a numerical mistake now. Okay, so he had a numerical mistake. He had a numerical mistake. So we learn that he made in 1778 a theoretical mistake. I'm not going to go into details what is exactly that mistake. And in 1778 C, he made a numerical mistake. So we chose that these are two most common mistakes. So Dinnick obtained, as I said, in 1912, P critical equals 18.6 EI over L cubed. That is for uniform or homogeneous column. Okay. This involves very difficult functions, special functions. Bessel functions and Lommel functions. Okay, and I'm not going to go through that. Yes, sir. Units? Oh, that's very easy. Okay. Oh, I said Q critical. Q critical is Newton over meter. It's dimension. So Q critical L equals 18.6 EI over L squared. So that is load. And this is Newton. So then we get familiar. Okay. So 9, 10. So what is our topic number now? No. $43, okay. So why did I say no? So in year 2000, I published the following paper, which is called like this. Euler's, so that is a topic. Euler's problem reconsidered. 2,220 years later. Okay, it is published in the journal Meccanica. That is Italian journal, volume 35, 375, 380, and you can download it if you want. Why I called it, why did I say 222 years later? Because if you remember, there is this book by Alexander Dumas, Three Musketeers, yes? Have you read this? Did you read this book? Say it again? Oh, you saw a movie. No one else read the book or saw a movie? Okay. So that, at least when I was a child, everyone would read this book. Later, it has a follow-up. It is called 10 Years Later. And then it has 20 years later. So it describes actually what has transpired with these Three Musketeers 10 years later than in the original book, and then 20 years later, etc. So I was inspired by the title by Alexander Dumas. Okay, so I will write down the differential equation. Differential equation will be d2 dx squared d of x d2w dx squared plus d dx q l minus x dw dx equals to 0. So why this quantity is coming into play? So if this is x, then what is important here, I mean inner force, is this value, n of x here. And this n of x equals q times L minus x, okay, which enters into this differential equation. At least I can explain you very fast like this. So you remember that I don't like to deal with dimensional equations. So I will have, look, d2d, so psi equals x over L. Why not? So then it will be L square d psi square. Then will be d of psi d2w L square d psi square plus dl d psi. Then will be q. Now L minus L psi. Then dw L d psi equals 0. So we'll get here L in fourth power. So there is this L, will be L in fourth power divided by L, will be L cubed. But then there is this L coming out again. No, this L and this L, yeah, but there is another L, yes. This L and L will be cancelled. And this L in fourth power divided by L will be L in cubed. d2 d psi squared d of psi d2w d psi squared plus q critical L cubed d psi 1 minus psi dw d psi equals 0. So that is a governing differential equation. And I'm again doing what I do before, postulate. That is my postulate. W of psi equals psi of psi, given function. So I just substitute and I get as follows. d2 d psi squared, d of psi, d3 psi, d psi, d2 psi, d psi squared, plus p critical L cubed, d psi, 1 minus psi, d psi equals 0. So that is my governing differential equation, and I know psi. I don't know d of psi. So I will consider simply supported case. How much is psi? I want to ask you. Say it again. I don't hear, sir. I'm asking how much is psi of psi? What should I postulate for simply supported case? I said that I know the displacements ahead of time. Before solve, I mean, I don't need to solve. To solve direct problem is very difficult. Almost impossible. You see, Euler made mistakes. Even Euler made mistakes. And it took 134 years to solve it properly. Then you needed to use very difficult functions. Okay? And since then, it was solved only by Bessel functions, Lommel functions, and finite element methods, nothing else. Now I'm saying, you know what, I know psi of psi. How much is psi of psi, Mr. Peguero? Sir, your name Peguero? No, so therefore you are not talking. Okay? Yes. As which beam? This is simply supported, but simply supported, look, I have now simply supported column and with this such a loading. I mean, for the problem. I'm asking, what psi of psi should I take? Mr. Fan? This we know. Student says that it should be in such a manner to satisfy boundary conditions. Yes, of course boundary conditions should be satisfied. Why would not? Why would we not satisfy boundary conditions? I want to know the function. I want you to give me the function here. Yes? Yes, psi minus 2 psi cube plus psi in fourth power. I'm taking the same function like in the previous problem. I don't care about the problem, is it not? Because I have my psi. I found already this psi. And therefore, I can use this psi in any problem where there is simply supported boundary condition. Okay? The same as in this case. The same. I will take absolutely the same expression. Okay, now I have to find how much is d of psi. Okay, so again, look please. Psi is a fourth order polynomial, so d psi d psi is a third order polynomial. Now then this one, 1 minus psi, d psi d psi, is a fourth order polynomial. Then first derivative of this is a third order polynomial. Okay, third order. Now here this is fourth order polynomial. It is differentiated 2 times, so it will be 0 order. So therefore d of psi must be a third order polynomial. It cannot be second order as before. So I have to write down d of psi equals b0 plus b1 psi plus b2 psi squared plus b3 psi cubed. That is what should be done. So we proceed. Okay, so psi, as we said, equals psi minus 2 psi cubed plus psi in fourth power. Psi prime, because here I have psi prime, equals 1 minus 6 psi squared plus 4 psi cubed. So then I have 1 minus psi. 1 minus psi times psi prime. That equals 1 minus psi times 1 minus 6 psi squared plus 4 psi cubed. This equals 1. First I multiply 1. 1 minus 6 psi squared plus 4 psi cubed. Minus psi plus 6 psi cubed. Minus 4 psi in fourth power. So that will be 1. Then psi, minus psi. Then squared, minus 6 psi squared. And this will be plus 10 psi cubed minus 4 psi in fourth power. Then I have first derivative. 1 minus psi prime, first derivative. That will be this gives me 0, this gives me 1. Minus 12 psi plus 30 psi squared minus 16 psi cubed. I hope I did not make a mistake here. You must be really looking well. Okay, here I have second derivative. So psi second derivative equals from here 0 minus 12 psi plus 12 psi squared. So that equals 12 minus psi plus psi squared. That is a second derivative. Then I multiply d of psi times second derivative. b0 plus b1 psi plus b2 psi squared plus b3 psi cubed times 12 minus psi plus psi squared. So this equals 12. So I will multiply this by every term and then this by every term. Minus b0 psi minus b1 psi squared minus b2 psi cubed minus b3 psi in fourth power. Then I multiply this guy plus b0 psi squared plus b1 psi cubed plus b2 psi in fourth power plus b3 psi in fifth power. So this equals 12. Okay, so minus b0 psi. And then psi squared. So it will be minus b1 plus b0 psi squared. So this I took into account in this. Then b cubed plus minus b2 and then plus b1 psi cubed. Then minus b3 plus b2 psi in fourth power plus b